Okay, so we have explored the electric field due to one charge, due to multiple charges. It's time to extend that and explore our calculus version of electrostatics again. I'd like you to note the similarities between the method that I'm using here and what I used in the force problem that we analyzed before using calculus. I also would like for you to recognize that this particular video is going to be really involved in terms of calculus, but we are going to show you a method to find the same result in this situation and situations like this that is much, much simpler and elegant. You can't always use the elegant method, but this is an example where you could. So we want to understand the fundamental idea behind how to use calculus. In this case, to determine the electric field at a point P due to the presence of a rod that is charged with positive charge. Here, where our rod extends infinitely up and down, we could truncate that if we wanted to, but I'm going to go ahead and let it extend infinitely up and down. And what that allows us to do is, well, truncated or not, if we find this point P at the center of the rod, then what that allows us to do is use symmetry. So that we know that all electric field contributions from the top of the rod and an equivalent place at the bottom of the rod are going to cancel in the y direction, but not in the x direction. So, well, let's go ahead and begin analyzing this. What we're going to do is use a charge density. This is a linear charge density. We're interested in, along this length, how much charge per unit length. We'll use lambda to denote that. It is equal to charge over length. We could also say it is equal to d amount of charge, incremental charge over incremental length. I'm going to go ahead and use y as my incremental length and set up a coordinate system where this is positive y and negative y would be below our horizontal line. If you don't like that, you could always use L or whatever you like, but since this is up and down, I'm going to go ahead and use y. Now you could also give, just to get a concrete feel for this, if you wanted to, you could give this a number, like, let's say, 80 nanocoulombs per meter, something like that, right? I'm going to go ahead and leave the numbers out because I want the method to be the most important thing here. Be nice and clean. Okay, so we want to go about this process again as though it were a single charge. So in order to do that, what we do is we select a single charge. I'm going to go ahead and select that charge right there. And then, or that length of rod, charged length of rod, which would be a length dy, right? Now, if I eliminate the rest of the rod, then we can look at this as a single point with a single amount of charge, dq. And dq will be along an element dy, right, in the y direction. Okay, so essentially what I'm attempting to do then is to sum up all of my dq's and their individual influences. So if I take this one dq here, I can immediately start to solve for the electric field due to that single dq. That's not so bad. I want to know what this distance is away from my rod. In order to label that, I think I'll use S because R is going to be used elsewhere. So frequently we'll use S. If you don't like that, you could always use something else. You could use a capital R, or you could even use a happy face if you want to, but I'm going to go ahead and use S. The reason that I'm using that is because R is going to be the distance that I show from let me get my gray out here, from here to here. In other words, the important distance that determines the strength of the electric field due to this small increment of charge, right? This is R. Immediately, we can see S is a constant, but R and Y will change together. We can see the relationship between R and Y. It's just the Pythagorean theorem. I might go ahead and write this as R equals the square root of y squared plus s squared. Okay. So we have R in terms of y. Let's go ahead and begin looking at our single, I guess I'm going to go ahead and call this dE. In other words, a small electric field due to the presence of this tiny little point charge here. This. And I'm also going to want x components and y components, don't forget. So I'll go ahead and draw those while I'm here at the drawing. There's my x, my y, and we'll get to breaking those down in just a little bit. This will be in the x direction. This will be in the y direction. Recall that we won't really need the y direction because of symmetry. So let's go ahead and write out our equation. This would be k times q over r squared, and we have to look at what our r is. In this instance, it's going to be this particular r here. That is gonna I'm gonna put a little I on there because that changes as dq changes, right? The charge that is producing the electric field is dq, and this is squared, and we have an r. Okay, so we would also be interested in only the x component, which would give us k dq over r squared, and we need some angle components. So we've got theta here, and that's the equivalent theta here. So that clearly would be the cosine of that theta, would be in the x direction there. Now we can rewrite this because we know that cosine is just, in terms of this triangle here, cosine is just s over r. And that's going to be really useful because what it allows us to do is get our angle theta. I want you to, when you look at these kinds of equations, I want you to look at this and this and this as all variables that need to all become one variable. We're going to go ahead and choose y as the variable that they all become. And which variable you choose sort of comes with practice. You can use different variables, but some of them are just easier than others. Okay, so this tells us then an individual element dEx, the x component of dE here, is going to be equal to k over r cubed, this is the same r, times dq. And then if we wanted to get all of the elements dE across all y's, then we just need to integrate. So now we can bring this back, and we're ready to take the integral of all of these to get a total amount of electric field in the x direction. This will be equal to, we can go ahead and pull the k out, because that's just a constant. Oh, I forgot my s. S. We also would have a, let's go ahead and write our s in there. We'd also have an s out front here. We have dq over r cubed. Now, we can replace the r cubed here. So I'm going to go ahead and replace r cubed with what would be the equivalent in terms of y and s. Recall that this can be written as 1/2. The root can also be written as 1/2. If we cube that, we would just get, instead of to the 1/2, to the 3/2. Okay, so we're getting somewhere. We have both r and theta in terms of y here. Our objective now will be to get q in terms of y, but we already have that relationship here. So we can rewrite dq as, by multiplying this by both sides, lambda dy. So we now have that the total x field is going to be equal to the integral. Oh yeah, I forgot to put my ks out front. That's a lot. I don't like that. Ks. Times lambda. Actually, we can pull that lambda out front too. Lambda dy over y squared plus x squared 3/2. Okay, again, I don't want you to have to dig through all of your calculus knowledge to solve this. We can always just grab this from a different source. So I'm just going to grab this from an integral table. Now, I identify this as a useful integral. The a here, it represents our constant s, and the x here represents our variable y. And so we can take this portion and equate it to this portion here. That means that the sum here will be ks lambda. Now we haven't put limits on our integral yet. Actually, let's go ahead and do that. This extends infinitely far up and down, but the correct way to go about that is negative a to positive a, and then take the limit as a approaches infinity. So we will go ahead and evaluate our integral. Our dy becomes y. Our s squared is here, and we have s squared plus y squared here, and that is to the 1/2. Okay. Now we're evaluating from negative a to positive a, so that's going to give us. Now I want to remind you guys that this. Just take a moment to remind you guys that this process is not simple. It's not. I mean, it is a little simple, but it's not easy. It's not easy to learn. And so I just want you to kind of try to understand this process, get a feel for it. Please recall that I am not going to demand this level of problem out of you on an exam, although you will probably have some homework problems that resemble things like this. Actually, the homework problems probably aren't going to be quite as difficult either, because of the limits of this thing going to infinity. Okay, so take a breath. It's okay. I know that this is a lot, but just hang on tight. All right, so we're evaluating a for our y, and we've got the s squared taken out, so we now have. I'm going to go ahead and write this as a root here. S squared plus a squared. And then we're going to evaluate as a negative a, so that's minus negative a root s squared plus negative a squared, which is still just, a squared, so no big deal there. The minus negative, of course, turns this into a 2a lambda over s. And then that gives us a over. Really, I should write this as limit as a approaches infinity. So I'll go ahead and do this with just a. And now, what I want to do, I'm going to go ahead and fix that. This is bugging me. Okay, now you may notice here that we're going to have a problem when we've got a upstairs, but you've probably worked with some limits in the past. If not, that's okay. Uh, like I said, this problem is tricky. What I'm going to do here is divide the numerator and the denominator by a. What that's going to do is create a 1 in the numerator here, and in the denominator, 1 over a, which I'll bring into the root. It's a very common trick in physics. Will be then, if I bring 1 over a into the root, then it's going to be 1 over a squared inside the root. So we would end up with s squared over a squared plus 1. That allows us then to take our limit and truly see it for what it is. This is not just bypassing an error of nature. What this is doing is revealing the true nature of this problem, where it wasn't so obvious before. What this means is that if we take this to the limit of a approaches infinity, this term goes entirely away. It goes to 0, very rapidly actually, so that we get Ex is now equal to 2k lambda over s. Okay, this again is an answer that we can actually get through a much more elegant method than taking the integral. We'll get into that very quickly here. It's called Gauss' law. So once we learn about flux, then I'll show you how this can be done in a simpler way. But this is a foolproof method for finding any geometry. The elegant method, Gauss' law, can only be used in certain circumstances. This one can be used in all circumstances, although sometimes it's a little harder than other times. So, to recap, what we've done is we've found one single element of a geometry that has a distribution of charge, determined what the electric field was to that single element, and that was here. And then we extended it to all elements along all distances and angles. We found one variable, y in this case, to translate our dq into, our r into, and our theta into, so that we could take the integral over one single line. Y seems to be the obvious choice, since when we take our single element here and we extend it to all the elements, you can see that dy is the most obvious choice of geometry. Theta is a little weird, r is a little weird, y is not weird. So that should give you like an indication that r is kind of a thorny path to walk down, theta another dark scary path, but y is a pretty straightforward path. Okay, and again, I want to remind you that when you're trying to take integrals here, make sure that you don't worry too much about figuring out methods of solving integrals. What you want to do is get it into a ready form so that you can look up integral table if necessary. And you shouldn't need to look up integrals like y squared. If y squared is in here, don't go look up that integral. You know that, right? Integral of y squared, you know that's 1/3 y cubed. That should be something that you'll get from calculus. But okay, if you got any questions, please let me know. Again, don't be too afraid of this. I know it sinks in over time.